I will talk about a new calibration for framework, which basically nested with the Bayesian optimization. And I did it with the very common World Food Study simulator. It's basically the Arable in modeling. And in future, we will extend this work to the livestock after the heat. So the thing is that this is the work. So initially, I will highlight that some of the insights that why um, the Bayesian nested optimization is needed with the calibration, and then I will discuss in briefly with the arable management model what have already discussed in details by the Brad Day. And then finally, our calibration with Bayesian optimization theory. So part of most of my initial slides are heavily theoretical. So, and with the algorithms, then I will discuss something about the what the parameter and inputs and how the OFOST works with some preliminary results. And finally, we the new approach what we have implemented between the two waves of history matching after so this framework is the active subspace methods in Android space. So these are the preliminary outlines of my talk today. So
Just before you start, you have to step back from the microphone.
oh here
So you can
oh,
hear.
yeah. Okay. So we aim to understand that how farmers make critical decisions about the crops, considering the weather effects and the environmental constraints. So environment and the economic constraints is that price, cost, and we also need to take the yield. So people going to the mathematical forms, I tell them in the last, if you saw the statistics over last 2 years, you will see that the UK's total income from farming is decreasing drastically. It means we have lost almost £1 billion from 2022 to 23, and over 50% of food is lost before leaving the farm. So I just integrated these two problems with my current problem. The problem is that because we need the good decision management choices. So management choices is that what time is the best time to harvesting and what should be the good amount of fertilizers and what should be the different events. So for that, in the farmer in a farm we have the farm model and the management model, and the farm model, this is basically simulates the yield. So if you saw that yield equation, which is the y is with the function of x is the crop starting date, and z is basically the sequential different dates of fertilization, and q is the fertilization amount. So in here in the O first we have four different q's and four different z, and theta I, the theta is the mainly is the soil parameters over here, and so and this shy, this is the crop parameters which is not open. So in future maybe we'll do these things, and wi, this is the weather. And so the thing is that we have good amount of yield data for different land parcels from the DEPRA. But the thing is that we have some information for the management, but we have very little information about the management data. The problem is that even for parcels, we have the management data. We don't know the values of X, Z, and Q. So if we don't know the values of X, Z, and Q, in practically we can't run the OFOST. So what we can do, what we have implemented the Bayesian optimization technique to calculate the X, Z, and Q, optimize the X, Z, and Q, and then feed that X, Z, and Q to the O4 simulator, and O4 simulator will generate the yield for us, and that we can use that yield for the calibration purpose. So this is in short the arable management model. Already Brett discussed that our intention is to maximize the utility. So the utility is basically the function of the profit. So here the phi ij is the profit function and with the risk aversion parameter. So the risk lambda, we don't know the lambda. So what we will do, we will calibrate that lambda parameters, and if you don't need to think about the calibration that what should be the good choice of the lambda values. So that means if we have the high lambda values, it means the profit is also high. So if you were low, just simple mathematics that things. So we are expecting that after calibration, our lambda's region should be on the upper hand. So upper threshold. And so if we calculated simple math over that utility, we can integrate the expected the utility with this weather. So, but the problem is that weather have 8 different variables inside, and if you consider the distribution of weather, I don't want to think about this anymore. So this is completely undoable and the computational resources. So we need to think wisely what we can do with the weather, because the farmers, they maybe know, okay, this is the winter wheat, so the best time to harvesting is October, maybe November, but they don't know what's the weather, because the weather have a significant impact of crop yielding. We know that. So the arable management model, we consider the weather, the current weather. So we have basically considered the 6 different years of weather because we have only data for the 6 different years. So if we calibrate 2022, so that means we need to consider the weather for previous years. So suppose like 2021, 2020, 1918, like this, and the associated probabilities with this weather. So that expected utility function can be written over that PM and utility function. This is basically the finite approximation of the continuous integral. But the PM, if you saw that PM is the probability which is integrated with the weather. So we cannot, the problem is that we cannot directly calibrate that PM because the PM, we know that the sum of the probability equal 1. And if we need to satisfy that type constraint and with these calibration parameters, it's a hard job to do. We can do it in the proper Bayesian way by taking the fryers and so on, but it's very hard job. So that's why we have considered very simple way of regression, logistic term of phi 0, which is 1 by 1 plus E minus gamma. So here, if the gamma values are close to 1, so that means the maximum uncertainty the farmers can believe that, okay, if the gamma equal 1, so we are 74% sure the weather should be like this. So, and we can consider the profit as a linear function of Pj. Pj is the price of the jade crop, and Hi is the area of the land parcel in hectare, and Yj is that yield, and the other terms of the profit function is related to the machinery's cost and fertilizing cost and so on. And we also can consider that our yield is normally distributed over the optimizing parameters theta and phi. So that means we are considering that our yield is normally distributed. So I'm assuming that after transformation of doing the optimization, our yield also should be very close to normal. And we can consider by transforming this in the previous equations, we can consider the profit function in that way, very compact way, the utility function. So if we consider all of our PM and PM notation with this utility function, the whole form of utility function can be written very simplex way. And we can, if we consider the very simple representation of that expected utility function, this can be written as ay plus b or alpha by py dy. So, and to make the integration easy, because this is a very complex integration. And another thing is that if you saw that m, so that m running from 0 to big M, small m, so that means we need to run the O for m plus 1 time. So that means if we have m equal 5, so that means our integration will be run for 6 times. And this is very complex in STEM, but the R package state mode makes it easy. So it uses the Gaussian quadrature, and Gaussian quadrature is a method of numerical integration methods. Is basically extracted the integrate point and the weight, and then multiply integrate point with the weight, which gives us the values needed for the expected utility. And so it's a simple problem then. Then we are going to the model calibrations after doing this. So the things is that our concern, initially our concern is about the expected utility. Then based on that expected utility, we generate the yield from the O4 simulator. So the calibration, before doing the calibration, we need to optimize the management choices. What I mentioned, the X, Z, and Q of my previous equation. And so for that, the object data model, they have very known equation things. So the dy equal eta y ij. This is a very common calibration equation. Is just this is the equation is this is very common equation. So that the calibration is basically the linking the reality with the simulated data. This is the main theme of the calibration, and corresponding to the observation error and the model discrepancy by considering the emulation mean and variance. So this is the calibration thing. So here, if you saw that the true yields are basically consider the best input assumptions. So best input assumption is that the combination of the inputs which basically gives the a match with the real data. So, and then eta can be expressed based on the yield and the model discrepancy. So here we need to calibrate the parameters lambda. So I think you have memorize the lambda is from our profit function, and gamma is the weather uncertainty parameters, and theta here is all the soil parameters from the O-first inputs. So we need to evaluate these things from the calibration. And so before doing the calibration, we need to use the Bayesian optimization. So there, the Bayesian optimization basically optimize the C. So C is the X, Z, and Q. So we have 1X, 3Z, and 4Q. So we need to optimize that C hat based on the different combinations of theta, gamma, and lambda. So when we get that, we will feed that optimized values to the O first. It will generate the yield, and then we can use that yield to do the calibration work. So because these whole frameworks makes it some complex, so we represent it as an algorithm, and then algorithm is that one. So this is, I need to explain is very simple way. So our main primary intention is to evaluate the expected utility based on the theta, lambda, and gamma. So just consider these things. We have C in the C1, just consider the first part, C1, theta 1, gamma 1, and lambda 1. So suppose C1 is X, Z, and Q. So we have 8. So if we consider the usual 10D dimension of the input space, so we have 10 into 8, suppose we have 80 different design points, and theta, lambda and gamma, here we have 13 in the O first, we have 13 different design points, so we have 130 combinations there if we consider 10D formula root. So that means if we consider C1, so C1 is all the 80s, but theta 1, lambda 1, gamma 1 is the first row of 130. So that means all the rows of the theta 1 will be repeated with the C1. So that means our C1, theta 1, lambda 1, gamma 1, this consisting one set of data, and Cn, theta and lambda and gamma n, this is consisting another set of data. So that means we have 130 set of data. So that means for 130 different combination, we'll optimize the C. So that means we have 130 set of C optimized from the Bayesian. And for that, we need to run the O first. If when we run the O first, because if you remember that formula that the O first should be sum over m of 0 to big M, so that means we need to, within the single data set, we need to run the O first for the 6th time. So that 6th time yield will be sum over this one of the data set. So that makes it, then when we everything is ready, we will basically discuss, feed that data. So that means with all of the every possible combination, we calculate the expected utility. So here our y is the expected utility, and then x is the C1, Cn, this is the x input. So we can build the emulator considering the x and y, and so then we will use the usual Bayesian optimization things. Now we build the emulator, we have the emulator mean and the variance. We can do the acquisition function. So the things is that I have studied why that called the acquisition function, because that function basically used to acquire the best point from the set of candidates. So that means you have already evaluated a set of values from the expected utility of your initial design, and then you will use the acquisition function, which basically return the best value based on the expected improvement. So that expected improvement will give you the best input. So that best input will then again feed inside the O first, run the 6th time, and that 6th time will return the, and with the Gaussian quadrature and everything, we can calculate the expected utility and do these things for every 130 set of data over this Bayesian optimization loop. And after that, doing everything and updating the emulator within the each iterations of that single frame of the data, we will get 130 set of optimized C values. So we will get that 100. So now we are getting, after doing this Bayesian optimizations, we will get 130 set of C values, but our theta is repeating. For C1 we have one set of theta, for Cn we have another set of theta. So our, and then based on this, that give us the highest expected utility. We will consider the corresponding C values as our best value for the Bayesian optimizations. So in the Bayesian optimization, when we do the deep GP, our emulation, our input space is 21. So it is quite a big for fitting the deep Gaussian process. So that's why we use the dimension reduction technique. So what's the active subspace and the difference between the other methods? Because everyone here knows the principal component analysis. So principal component analysis is basically works with the inputs. But the active subspace, this is basically the linear combination of the input, which basically make the causal effect to the output. So it's consider both X and Y. So here The Z is basically the W1x1 plus W2x2 plus W1xn. This is the linear combinations of the inputs. So suppose we have 21, but all the 21s is not doesn't have actual same effect for causing the Y. Maybe combination of 2, 3 is enough for the yield. So we can generate the latent hypercube design for X, and then we can calculate the gradient based on that X. So there are different methods to calculate the gradients corresponding to the X. I'm not discussing the method because we have new approach considering that our Bayesian adaptive regression spline methods, which I will discuss later on. So that means we can, if we calculate the gradients, we can calculate the corresponding covariance matrix C by considering that from these things. So suppose the method what I am doing B Mars is basically using the MCMC samples by using the reversible jump method, and then if we can calculate the C, so we can consider the eigenvalue decompositions, and then the largest eigenvalue or cumulative variance gives us the indication that how many combination we can take for the active subspace method. So this is just the simple approach for doing the active subspace algorithm. And later on, now I have already discussed the Bayesian optimization technique. So I have already mentioned that we need to optimize C for each of the combination theta and theta n. So that means I have already mentioned that O first have 13 inputs to calibrate. So that means, and because we considering the 10D formula, so that means we have 13 dimension. So we can consider 13 into 10, and which basically gives us the C matrix by using the O first. So this part is already finished. So when we optimize the C and with the corresponding theta values and the weather, we can feed it to the O first model, and which basically return us the yield, and then we can consider the implausibility based on that yield. So dy here is our observed yield, and we consider the yield from a northern Berlin, which is around 7,130, and the E is the mean of the emulator, which will be will considering the yield from that optimization, and the in the denominator is the variance of the yield and the model discrepancy and the observation error. So we consider that the value less than 3 is good. That means the parameter combinations which gives us value less than 3, this is the non-implausible samples. Now the problem is going on when in the second wave of history matching. The second wave is that now the parameter combinations when you need to consider is basically the samples we need to take from the Android space of the first wave, and we need to repeat that from the procedure from each of the Android space, just like the first wave. And the second wave is to just do the Bayesian optimization, repeat the whole things for the Android samples. So when we can, and that will eventually give us the big large samples with the Android space after a couple of waves. And we have performed the O4 simulator. O4 is basically takes the inputs, fertilization, initial crop, and the crop rotation and soil. So we'll feed it all the things in the simulators, which basically gives us the output, and we daily output we just consider the maximum of the year, which is our final yield. And these are the input parameters what we are using there. So input parameters is that the WAP, this is the initial amount of water, and that assembly is the initial soil moisture, and we have three different fertilization, initial fertilization in the things, and the most two important input is the wilting potential and field capacity. The wilting is that the point where you cannot extract the water from the soil, and is have heavily relationship with the SM limb. And we have other input variable. This is critical soil and maximum percolation rate to the subsoil and the depth of the soil. So all of the inputs, they are highly correlated to each other because they are basically the soil parameters. And this is the diagnostics of the Bayesian optimizations. So we did that when this is in the x-axis, this is the sum of the Qs. So this is the different events of nitrogen. We just converted it to the kg per hectare, and in the y-axis, this is the yield. So we are treating that if we increase the fertilization, our yield will be increased. So this is the agricultural property. So that means it satisfies the things. That means our method is okay. So optimization is valid. And this is the restrictions over there, that we have imposed the restrictions that the sum of our Q values cannot go more than 0.25, and so restriction is fulfilled, and the samples have so many variations, so that means it's working. And the yield, what we consider, that the yield should be normally distributed. When we, after considering the optimization, it shows that our yield is basically normally distributed. And this is the optimization, the calibration result. I've already mentioned that we have 7,130 yield. So that means in the upper panel of this plot is the optical depth. If you show this is gray color, so that means in that space you cannot match the yield, the combination of the inputs. And the lower panel is the implausibility. So I'm discussing the upper panel. So if you consider that plot, SM limb and the water, so that means if the water content is low and SM limb is low, that means we cannot attain the observed yield of 7,000. So that means is mentioning that our yield, if we want to match the yield of 7,190, we need to consider we cannot consider the high yield and high water and high soil moisture. We need to consider the moderate level of soil moisture and water content. So all of the things look similar trend because of the high correlation. And we have, I'm going to run in just 2 minutes. Okay, so basically the whole work is for the 2 papers. So and so in the when the first we've done the existing method, what we are doing, the existing methods generate the samples whole over the input space rather than in our Android samples. So if we want to do the history matching of the second wave, our sample should be on that space. But the existing method, what I am doing, this active mass regression model, which is consisting of the this sine and the not functions. I'm not discussing it in details. So that function is basically generate the samples all over the region rather than in our short Android space. So what we have done, we consider we try to extracted that values from the existing method so that we can calculate the first difference to calculate our C. So we have imposed a algorithm for the adjusted active substrate methods. So for
Might have to move on to the results slide.
yeah. So that thing, we have loop over all the MCMC samples and the loop over all the NROI samples is basically this methods. So the results is that when we done the different wave of history matching, you will see that the new methods that we can reduce the parameter space good amount of, if you 88 and 81, 84 and 95, and building the emulators give the NRMC is lower with our new approach. And if you saw this plot, this is the same thing that we can our new methods is getting can cut the parameter space more. And this is the things where I'm telling you that the gamma and the lambda values cannot be 1. So if lambda values become 1, so that means the profit is infinite, 1 minus 1 infinite. So this is getting not 1, and the gamma values also gives us the 1. So if it's 1, so we can consider 73% of the things. That means after the third wave we get the same results. So this is just like this is the same plot of my first wave. We are reducing the further parameter space. And this is the final things. It's finished.
Oh, stop it there. This is great.
Yeah, so
I donate him.
Well, it's up to you.
yeah.
Nobody's
So-
scared of me, but I might scare of you.
So this is the thing, because the whole work is basically because this is very long work, and we have I think we will submit these 2 papers within next 6 months. This is our things, and also we have done the problem in the only individual land parcels. We can extend the work as the farm level. So that's it from my talk.